Let's start. Any questions, firstly? Okay. We're going to continue on the topic I had started last Thursday, namely starting to look at timing, and we'll get into details on what kind of requirements on the delays through the circuit need to be met for the circuit to work correctly, and we kind of saw some of that on a very intuitive basis throughout the course at various points, but now we're going to look at it much more formally. So I was going over this example, and just to refresh your memory, kind of the basic issue is the following: that at the clock tick, the state register changes; it gets a new value, and then the effect of that change propagates through our combinational logic. And our goal, one of the goals, as you might imagine, would be that the new value of the next state should be ready before the next clock tick comes. Okay, or more generally, if I expect the clock tick to uh, result in a value being stored into the flip-flop, then we have to make sure that the value is ready. Otherwise, the clock tick would miss. So there's kind of a race between the data coming through the combinational logic and the clock tick. If I'm going to latch something at the clock tick, then I have to make sure that the data is ready prior to that. You might also imagine sort of another situation which might happen, which is I'm sending the data to some other flip-flop far away on the chip, and the clock at that flip-flop may not arrive at the same time as the clock did in my system. And so I can also run into the reverse problem, which is my data may reach. I was hoping this data would reach after the clock tick, but it actually reaches before the clock tick at the remote end. So you can have both problems in both directions, because again, clock is also a signal, travels over wires, and wires have delays. Wires have delays because of what? Anyone? Why would a signal, what are the factors behind a signal taking delay through the wires? Huh? Capacitance. Okay, so firstly the speed of light, obviously. Okay, but it's resistance and capacitance. So resistance, capacitance, in those of your E in your circuit classes, you might even see things like RC delays. So it's basically that. It's a long line, and in fact, in modern circuits, the RC delay, the delay through the wires dominates the delay through the gates. Okay, in the sense that if you look at the overall delay budget, like the work we are doing in a single clock period, most of it is actually devoted towards the signal just traversing. Our chips are big, like the big Intel processors could be 3 centimeters to the side or something like that, so they could be pretty big. And at the same time, our gates have become very fast. And another thing is that as wires, as we shrink the devices, as we shrink our chips, wires get thinner. As wires get thinner, what do you think happens to their resistance? Goes up, right? Thinner wire, so less conductance, and therefore the RC delay goes up. Okay, so essentially delay dominates. Okay, that's kind of the long story made short. Okay, so wire delays do matter, and we'll kind of in this simplistic analysis in this slide set, we are going to ignore that for the most part. We're going to focus on circuit delays only. Okay, but you can imagine that wires could be similarly modeled as well. Okay, so main thing out here is that when we look at the activity that is triggered by a clock tick, there are several pieces of the delay. So in this canonical view of a sequential system that we have, when the clock tick happens, whatever was the value at the input of the flip-flop gets lashed into the flip-flops, gets remembered, and then will appear at the output of the flip-flop. Now that's not an instantaneous process, it takes some time, some small time nevertheless. Then this value in this particular example will propagate through. So it will kind of go out of this count, come back, go through the incrementer, go through the mux, and then appear. So we'll have all sort of combinational delays. In this case, the incrementer, the multiplexer, and of course the pieces of wiring that exist between them. And then what we have to make sure, so that's the effect we were seeing out here, which is there was a flip-flop delay out here, and then there was a delay through the logic. So by the time the next value is ready, some time would have passed. Now in this example, it's okay. The next value is ready out here, and my clock tick does not come until that point, so that's fine. But if we were aggressive on our clock cycle, if we made our clock cycle faster, then we can run into trouble. So as you might imagine, what this says is that given a circuit, given certain delays to the combinational logic, there will probably be a fastest possible clock speed I can run at, because if I run any faster, then the period is going to go down, and then my next state will not be ready in time for the clock tick. So we'll see how to deal with this thing later. Another thing to bear in mind, and that's also very important, is the following: that in diagrams like these, we often draw signals as a bundle, multi-bit signals as a single wire, right? So for example, if you look at like this line out here, okay, it really is n different signals, okay? And there is no particular reason that the delay that this incrementer is going to provide is the same for all those bits. It could be that bit number 0 gets ready quickly and bit number n-1 does not get ready until much later. So when we see a multi-bit signal, then different components of that multi-bit signal may change at different times, okay? So at some point in time, I had a good clean value, n-bit value, and then the bit starts changing. But since they don't change together, so there will be a period of time where I might actually go through intermediate values before I settle on the new value when I look at the n-bit number. So let's say I was going from all zeros to all ones, unless it so happens that all the bits change simultaneously to 1, 1, 1, 1, I'll go through some intermediate combinations before I settle on 1, 1, 1. And of course, as you might imagine, in physical reality, they will never happen simultaneously, probability 0. Okay, so the norm is that you are going to see some duration of time while your signal is kind of changing. So something worth keeping in mind that it can be misleading the way kind of schematics are drawn. It seems like a single signal, but it's really multiple signals that are that exist. So for example, this is some an implementation of the incrementer, which is just in terms of half adders. And what might happen is each one of, if I look at each one of these stages of this half adder, this is the circuit from several weeks ago, then as we add 1, the signal is kind of propagating through the carry chain, and the lower bits, as you might imagine, will settle sooner. The upper bits are going to take some additional time to settle. So when we talk about the delay of something like this, a multi-bit entity, then what we are really saying is the worst case delay, the delay in which the delay needed for the time needed for the longest the output with the longest delay to settle, okay, even though some other bits may settle sooner. Now we'll see that even this thing does have a role to play, because what it is saying is there is a window of time. My signal starts changing as soon as the output of this half adder starts changing as soon as the lowest bit likely is beginning to change, but it may keep being unstable, and then only when the uppermost bits have also seen their final value would kind of the overall signal be stable. So there's going to be an earliest time and there's going to be a latest time associated with the output out here. So we can see that if you kind of if you were to kind of analyze individual bits. So this is the same circuit that we had previously, except that I'm kind of running it in a 2-bit mode. So next 0 and next 1, except that now instead of looking at the signal next as a single signal, we are really looking at its two components, next 0 and next 1. And at the clock tick, at this point, things start happening. After a little while, count changes. So that's the delay. So this delay is a delay through the flip-flop. And then this count propagates through the incrementer. And when we look at the incrementer, as we just saw, different bits in the incrementer see different amount of delays. Then it goes to the multiplexer. Multiplexer is usually fairly close to even delays for all the bits, so we are not going to see anything different. But now when I look at this next signal, what you see is that next 0 is settling sooner than next 1. Okay, so I was originally at 1 0 or rather 0 1, so next one is 1, so 0 1. We are adding 1 to it, so the output should be 1 0. But if you see, we are going through this intermediate stage where the next 0 has changed to 1, changed to 0, and this is still 0. So instead of going from 1 0 to 0 1 in one go, we are going from 1 0 to 0 0 to we are going from 0 1 to 0 0 to 1 0. This is kind of a similar issue which we saw way earlier in the course. You might remember I talked about glitches, okay, where we were talking about that how the output may change before stabilizing. It's kind of a similar phenomenon, but reason is different. The reason out here is that I have multiple bits and they're just seeing different delays through them. So these regions where the signal, a multi-bit signal, neither has the old value nor has the new value, usually in these kind of timing diagrams are shown as this kind of a shaded thing. So essentially we are saying that there is obviously some digital value there, but it's some gibberish that we don't know, will depend upon the very specific delays that are being observed. So this is basically a way of indicating that. Okay, so now let's talk about the delays more formally. Okay, so let's say I have a combinational logic. It takes some A-bit signal and produces some B-bit signal. Now, when A changes, then potentially, when the input changes, so these are so let's just some n-bit signal here, some m-bit signal here. Okay, when A changes, after some time B will change. In fact, if you recall from Salma's presentation on Verilog, when she talked about how to represent combinational logic in Verilog, a comment she was making was that the combinational logic is as if anytime any input changes, the output changes. So when I write a combinational equation in Verilog, like let's say some function f, I'm going to pick something. Let's say x, y is output is whatever, something z. Okay, let's say I have f is a combinational logic function. One way of thinking about it is that since combinational logic is a piece of gate, then whenever x changes, z can change. Whenever y changes, z can change. So it's almost like what I have is an entity sitting there monitoring the inputs, and whenever any input changes, it recomputes this output immediately. Okay, that you can think of a combinational logic in that way. It's a hardware program, whatever way you might want to think about it. What it is doing is it's just continually monitoring x and y at all times. And whenever x changes or whenever y changes, it recomputes f and dumps it on the output. Okay. So in Verilog, we accomplished that by making the sensitivity list the always to be include everything. So so combinational logic you can kind of view in that fashion. So looking at out here, I have a combinational logic. I have multi-bit signal A coming in. This piece of hardware is always monitoring those bits, and whenever those bits, any of those bits change, one or more of them changes, it immediately kind of conceptually recomputes and creates something on the output. Furthermore, as we saw in the previous slide, since my output is multiple bits, so it could be that some bits are computed or get get known sooner, and other bits get known later. So now if I look at these signals A and B, and remember A is also coming from some other digital logic. So in general, what they would look like is that A will have some old value, and then A will get some new value. Once it's changed, some bits of A change. And likewise, B had some old value which was equal to f of A or whatever the function was, and then at some stage B will get a new value. But in between, there's going to be some period of time when the signals are changing. The bits, some bits have changed, some haven't. So the value is really neither old nor new, it's something else. So what we have really are some definitions out here. So T1 is the T sub 1 is the time at which the input signal A began to change. One or more of its bits changed. And T3 is the time at which all bits of A had settled to a new value. Okay, so between T1 and T3, the input was changing. Okay, before T1 it had the old value, after T3 it has the new value, in between it has something that we don't know. Likewise, for the output, T2 is the output, T2 is the time at which the output began to change. If our combinational logic was an adder, then probably the lower bits began to change. Okay? And finally, T4 is the time at which output became stable, and after that, if A wasn't changing, then output will also not change. Okay? So T1, T2, T3, T4, these are 4 times. You know, question?
Yeah, why is it for the subscripts for T, C, A, B, and D?
I haven't come to that. So we are just focusing on T1, T2, T3, T4 right now. Okay? So T1 is when A began to change, T3 is when A finished changing, T2 is when output began to change, T4 is when output settled. Okay? Now these are just going to be like the setup of your system, right? I mean, A is coming from outside world. So what is T1 and what is T3 is not really under your control. The entity supplying the input to you is deciding that. And T3 and T4 are the characteristics of your circuit, right? What is T3 and what is T4 will depend upon your circuit. Now, there are two very important definitions which result from it. One is T sub CAB and the other is T sub DAB. So, T sub CAB is referred to as contamination delay. Okay, so this is T sub CAB and this is T sub DAB. We refer to T sub CAB as the contamination delay, and its definition is the following: time from the first input change until the first output change. So kind of the idea is that at T1 the input became contaminated, and at T2 the output became contaminated. It started changing. They haven't gotten the new values, but they started changing. So think of them as they got contaminated. So T1 through T2, that is this delay, we call as contamination delay. Now it's clearly a characteristic of the circuit. Anytime something started changing at the input of my circuit, then sooner or later the output will, one or more bits of the output will change. And that delay is defined as contamination delay. And propagation delay is time from last input change to last output change. So it is from T3 to T4. So it's basically saying time when input settled and is no more changing to time at which output settled and is no more changing. Okay? So in effect, T4, after T4 output is settled and after T3 input is settled, and we turn these things. And again, these are just characteristics of my circuit. There is whatever that difference is, we are going to experience that every time I kind of have some change in the input, which results in a change in the output. So again, propagation delay is time from the last change in the input to the last change at the output, and contamination delay is time from first change in the input uh, uh, to the first change in the output. Okay. Any questions on this? Okay, so again, this is just sheer definition at this stage, but we'll see the role kind of it plays out. Now, real circuits have an additional complexity also, which is signal voltages do not change instantaneously. So when I look at a piece of wire and if it's going from logic 0 to logic 1, so let's say 0 volt to 3 volts, then it's not as if 0 volt can change to 3 volt instantaneously. It takes time, it's a physical signal. Were it to change instantaneously, then you basically are talking about infinite amount of current, right? dV over dt would require a lot of charge to be moved immediately. So it's going to change at some leisurely pace depending upon the resistances and the capacitances in the circuit. So what you normally see therefore is if I look at a signal A or a B, then at some stage it was 0, at some stage it becomes 1, but instead of changing like this, it is really changing in a leisurely fashion like this. So that introduces this additional complexity that how do I define delays? Like if even one bit of A is going to take this leisurely amount of time, what do we say that when did it begin to change? So usually, as you might kind of expect, we pick the 50% point. So when we are measuring delays, we measure them from 50% point. Okay, and we usually make a distinction between falling and rising. This is T sub PR and T sub PF. So basically, it turns out that the circuits are asymmetric. Usually, the delay when the output bit is falling is different than the delay when the output bit is rising. So we give them different sort of terms. TPF is the propagation delay when output is falling. TPR is the propagation delay when output is rising. Now, one thing to remember out here is here I'm using the notation TP. I'm not calling it at TCAB and TCAB and TDAB, and the reason is the following. Remember, TCAB and TDAB were happening because I had multi-bit signals. If I look at a single bit, then some point it would be 0, it will rise and become 1. There is no ambiguity other than this kind of small amount of rise time. So the reason we were seeing these gray zones, these zones out here and this zone out here, is because generally speaking, input and output are multi-bit signals. Some inputs may change sooner than other input bits. Some output bits will change sooner than the other output bits. But on the second slide, we just have a single inverter. So these signals A, B, N, and C, these are single bit signals. So they will change cleanly. They are 0, they'll go to 1, and they'll have some sort of a rise or fall time. So I don't have to worry about contamination and propagation delay out there because they're one and the same. When A gets contaminated, it's also both the earliest time and the latest time because it's a single bit signal. So this is falling delay, that when output is falling, and this one is rising. So TPR and TPF because the font is small size. Yeah. So these are two additional terms. At a single bit level, I can talk about rise time, the delay when output is rising and the delay when output is falling. Okay, so we have seen kind of basically three concepts then. Contamination delay and propagation delays, and that arise because we deal with multi-bit signals and some bits change sooner than others, and then just this standard propagation delay where I'm not worrying about multiple bits. Basically, there's contamination and propagation takes the same amount of time. So real circuits. One other thing which I have not shown out here, but another parameter for real circuits that we also talk about is the amount of time it takes the signal to go from 0 to 1. Okay, and usually it is measured from the 10% point to the 90% point, or vice versa. So at the point the signal reached 1/10 of the eventual voltage, to the point in time it reached 90% of the eventual voltage. That time which is here, so this would be 10% point, and this would be 90% point. That we refer to as a rise or fall time. So this is simply referred to TF, and there will be the counterpart TF. Rise and fall time are also important, because if rise and fall time are very sluggish, then my signal is spending a lot of time in this kind of intermediate voltage range, which is not good. Rise and fall time also have other implications. So very short rise and fall times are also not very good. And so you might intuitively think they would be great. I mean, why would I not want a perfect rise time, kind of close to zero rise time? Anyone? Why would it be not a good idea? What issues do you think can come up if rise and fall time are very rapid? Huh? True, in high-speed circuits you can begin to see issues when you have very high rise and fall time, so you have some transmission line effects and you can have some bouncing around. So that's one reason, okay.
I was thinking it might not be easy to tax those edges.
No, I mean, if actually from the perspective of a flip-flop, it would be great if the edge was good. So one reason is indeed what he said, which is when you have very rapid rise and fall time, then you basically start entering into a regime where electromagnetic effects become very prominent, okay? And in a sense, your signal, instead of cleanly going and settling at 1, it will overshoot, the voltage will become high and then kind of oscillate a little bit before settling. That's not good. The second reason, which I alluded to earlier, if my voltage is rising very rapidly, that is saying something about the current movement. So instantaneously, I'm going to see a big current spike. And the third reason, which relates back to the second reason, is that if I have a sudden rush of current draw from the power supply, then it has many bad effects which happen. One bad effect which happens is that if I have this large change in current over a short period of voltage over a short time, so large current, then if anywhere in my circuit I have inductances, which is the third passive circuit, R, C and L. So inductors, the way they work is that if they see a derivative of current, di over dt, then that translates into voltage. And it turns out that inductors are present in power supply lines. So when there is a sudden draw of current, we suddenly see a voltage drop occurring on the power supply line, and therefore my circuit, instead of seeing a good voltage, is suddenly seeing a noisy voltage. So very sharp rise and fall result in noise on the power supply, which makes the circuit less robust. So that's one issue. Those of you who do circuits, you'll probably study about it later. At the other issue, which is a related one, is when there is a sharp change in current and all, it results in generating the same noise that I was just talking about. That noise can then be emanated into the air. And so you see what is called as electromagnetic interference, which basically means when your device is operating, it's generating all sort of radio waves and causing interference around it. This is why, among other reasons, for example, it used to be that, or still are, that during landing and takeoff and all, they make you shut your electronic devices, because kind of the idea is that these devices, as they run, because they're usually not very well designed, and also they generate all sort of radio waves around them because of this effect, and that causes interference to avionic systems and all. Okay, so that's another reason. So fast is not always good. I guess that's the moral of the story out there. You want them fast enough, but no faster. So back to our conversation, our discussion out here. So now let's look at how do these contamination and propagation delays behave. So there are a couple of composition rules that exist. One is if circuits are in series. So if I take a combinational logic and take its output and feed it to input of another combinational logic, then what it says is that propagation delay and contamination delays both add up. Okay, so if it is in series, So in effect, contamination delay would be the sum of the contamination delay of this big circuit, the outer circuit, would be the sum of the two internal circuits, and likewise the propagation delay. And you can kind of intuitively verify from the diagram, which is there, follows from the definition. Things get trickier if I have circuits in parallel. So if I have two gates in parallel or two circuits in parallel, I feed some common input to both of them, and then they come together eventually at the output. So my output depends upon an input through two different paths through the combinational logic. If that happens, then the way it works is the following, that you should look at all possible paths which come from an input to an output through some different set of gates. We'll see an example shortly. And then what it says is contamination delay is the minimum of all the contamination delays we see across the different paths. And propagation delay is the maximum that we see across different paths. So let's talk about it, because this is a little bit less intuitive than the serial one. So let's say I have this circuit. Okay. So the output F depends upon A, for example, through two paths. I can start at A and I can go through this top gate and then go to F, or I can start at A, go to this bottom gate and then go to F. So there are two different ways A can influence F. And what this previous slide said was that I have two paths. For each one of these, I can figure out contamination delay and propagation delay. But if I'm looking at this overall circuit, then the contamination delay from A to F is going to be the minimum of the contamination delays along those two paths, and propagation delay is going to be the maximum along those two paths. And intuitively, remember, contamination is saying something about the earliest, so minimum. Propagation is saying something about the latest, therefore maximum. So for propagation, take the maximum of the two. For minimum, take the minimum of the two. What about the two paths themselves? So if I look at the path which is going from A through D through F, I have two gates in series out there, right? I have the top AND gate and then I have the OR gate. They are in series. And we already talked about that for series, both propagation and contamination just add up. So therefore, when we are going from A through F, the propagation delay is going to be the sum of the propagation delay of AND gate and OR gate, and likewise contamination delay would be the sum of the two. Now, these things are just AND and OR gate. So their contamination delay and propagation delay are really one and the same, because these are just dealing with 1-bit signals. We are not dealing with multi-bit stuff at that stage. So looking at this, what we see is the following, that my signal A changed at some point in time. These numbers 3 and 1 and 1, these are indicating the delays of these gates. And remember again, for a single gate dealing with just 1 bit, 1 bit values, the propagation and contamination are one and the same. So when we say that this AND gate has a delay of 1, we are basically saying that if I look at any of its input and the output, then both the contamination delay and the propagation delay is 1. Okay. Likewise, for this NOR gate at the bottom, it is 3, and for this OR gate here, it is 1. So contamination and propagation delays for the primitive gates are the same. Okay. So now we have two paths, ADF and AEF. So if I look at ADF, it's going through the AND gate and the OR gate, and therefore the contamination delay is going to be the sum of this 1 plus 1, so that is 2. And propagation delay is going to be the sum of the two also, so it's 2. If I look at AEF, then same thing is 3 plus 1, so that's 4, and propagation delay is 4. So if I look at those paths separately, because again I'm just traversing a single bit signal through, propagation and contamination delay are one and the same. But now if I'm looking at this overall circuit and I'm saying, I try to say what is the contamination delay from A to F and what's the propagation delay, then contamination delay of A to F is the minimum across all the paths. That would be minimum of 2 and 4, so there's 2. Whereas propagation delay is going to be the maximum of the two, and that is 4. And in essence, what it is saying is the following, that look, A can affect F through two different paths. When A changes, then the earliest it can affect F is the shorter of the two paths. And then when A settles, the latest F can settle is the longest of the two, longer of the two paths. So that's really the effect that we are kind of seeing out here. The other two signals, B and C, are just have one path, so we don't have to worry about it. But nevertheless, what do you think is the contamination delay of BF? From B to F, what is the contamination delay? 2. It's going to a top gate, AND gate, OR gate. What about propagation delay? 2, right? Because it's a single path. What about C? What's the contamination delay? 3 plus 1, 4, right? And propagation delay, same story. Okay. So what we have seen thus far is several sort of concepts already. Individual gates, propagation delay, contamination delay is the same. And usually these gates are symmetric, so from any input to output, the delay is the same. So if I have an input AND gate, the delay from any input to the output is the same. That's the first order reasonable model. Once we have multi-bit signals, we start entering into contamination and propagation delays being different. And also when we have signals which traverse through multiple paths, as we see in this example, where A to F, there are two paths involved. So again, we start seeing contamination and propagation delay being different. What we also saw is that if I give you just combination logic, if they are in series, the delays add up, both contamination and propagation. If they are in parallel, then we take the minimum or the maximum, okay, depending upon which delay you're looking at. So, any questions on this example before I move on?
Could you explain again why the delay for C was 4?
Why did I get it wrong? Oh, okay. So C is basically has just one path going through the bottom NOR gate and then through the OR gate. They are in series. Therefore, contamination delay is going to add up 3 plus 1. Propagation delay is going to add up 3 plus 1. Okay. So let's look at this guy. So B is simple. So in this case, the numbers, the delays for the primitive gates are up here. Okay. So let's start with, what do you think is the contamination delay of B to Q? Anyone? Or take a shot? Someone from the side? 55, right? You just add them up, right? Okay. What about propagation delay? From, again, B to Q. It would be the same. There is a single path, right? So it's 55. So let's move to the more interesting case. A has two paths, one going like this and the other going like this. So let's look at contamination delay, TCAQ. So what's the strategy? I have two paths. So my contamination delay is going to be the minimum of the contamination delay of across the two paths. So min of upper path is what? 25. And lower path is 10 plus 20 plus 10, so there's 40 plus 20, 65. So contamination delay is 25. And propagation delay is going to be the max of the same, and therefore it's going to be 65. Okay. and of course, this concept you can imagine CAD tools can do this kind of delay analysis giving a circuit. Of course, those circuits are going to be a lot more complicated, but it's some graph algorithm which can kind of do all this stuff. Okay. Let's look at something more complicated. So what we have out here is a full adder. So you see A, B, and carry in, and we have carry out and sum. And we are interested in the propagation delay from A to S, contamination delay from A to S, propagation delay from carry into C to S, carry into S, and carry to carry. Okay, contamination delay. And what we are given is NAND2 has a delay of 80 and OAI21. So it stands for OR and invert 2 to 1. Okay, so what it is actually referring to is this gate. It has an OR gate, it has a 2-input AND gate. So it's OAI, there is an inversion happening. Okay, so we see this gate being used multiple times out here, here, and this guy. So this whole design is actually made up of just 2 types of gates. It's made up of 2 NAND2 gates and 3 OAI21 gates. Okay, and what we are given are the propagation and contamination delays of each one of these. NAND2 is 80 and OAI21 is 120. So let's look at what TDAS might look like. So TDAS, one path is going to be like this from A to S. A second path is going to look like this. It goes through the bottom part of this gate. Okay. Do you see any other ways of getting in there? Not really. So these are pretty much the 2 ways I can get from A to S. So I have 2 paths, and then I have to play the same game that we talked about before, which is take the min of the contamination and max of the propagation. So we can do that. So the way you could approach this thing is the following. I can look at what the minimum delay to various signals that I have. So G prime, P prime, which are internal signals, C out, U3, which is out here at this point, and then S, which is out here. And we can look at what is the minimum we are going to see from starting from 2G prime starting from A or B. So if I look at G prime, it goes through Q1, and therefore I have an 80 out here. And from C in, I cannot get to G prime, so there is nothing there. Second row says, what is the minimum time to P prime? Well, starting from AB, and we are trying to get to P prime, which is out here. So I have to go through, I have 2 possibilities. I have to go through yellow path or the green path. Through the green path is 120, for the yellow path is 80 plus 120, so the minimum is going to be 120. And I cannot get to C in from P prime. Next we look at C out. So C out is out here, and to get to that from A or B, I can only go through a path which goes through Q1 and then G prime and then Q5. That would be 80 plus 120, so 200. On the other hand, if I'm going from C in, then from C in I have a shorter path like this, and therefore it is 120. And likewise for U3 and likewise for S. Upshot of all of this is that from AB to S, minimum time is 240. And from C into S, minimum time is 120 across all the paths that exist between this scale. And likewise, I can do a max analysis, which will result in this. So for example, if I look at S, there are 2 paths, right? So the yellow path goes through 80 plus 120, that's 200, plus another 80 for Q3 and another 120 out here. So that's a total of 400 on the yellow path.
and 120 plus 120, which is 240 on the green path, if I go from A to S. Max of that is 400. And for each one of these, I can each of these internal and output signals, I can do the max analysis also. Now we have the min and the max. Looking at that, now we can talk about TDAS. TDAS is the maximum across all the paths from A to S, and that we just computed. That's 400. TCAS is the maximum across all the six paths from carry into sum, and that we calculated to be 200. TDCS is propagation delay, and it's the max across. Sorry, I think I messed up. This is TCAS. So this is contamination from A to S. So I will be looking at 240. TDCS. TDCS is the maximum from carry into sum. So that would be this guy, 200. And then TCC is going to be minimum from carry in to carry out, which is this guy, 120. Looking at this, what you can also say is if I create a multi-bit adder, then at every stage, I'll have a delay of 120 nanosecond as I go from one bit to another because my carry is propagating through. So if I make a 32-bit adder, it would be 32 times 120 nanosecond plus a little bit more. So faced with arbitrarily complicated combinational circuits, you can kind of just gradually build up these propagation delays and contamination delays and get these values for every possible output. Okay, so main points remember at this stage. Contamination delay is not the same thing as minimum delay. When we refer to minimum delay, we are basically referring to the minimum propagation delay. Whereas contamination delay is basically saying something about the earliest change to the earliest change. So that's one point to remember. And so contamination delay is the minimum amount of time from an input signal to an output signal, whereas minimum delay is the minimum amount of time from an input change to an output changing its correct value. So you'll often see minimum delay, that's kind of a different term. So contamination, propagation, and how to compute them is something that you should be pretty comfortable with. Okay. But it's a lot of this bookkeeping, basically. Okay, once you following just the definitions and all. Yeah, question.
Can you go back to the ladder?
Okay.
Why did we use like unnecessary inverters like in the outputs to the inputs of the first gate? You know, they're not.
Where are you talking about?
We inverted the A. You see the gate, the first gate.
This NAND gate.
Yeah, NAND gate, and then we inverted back.
Here.
Isn't that will add a delay?
So anyone wants to comment on that? Why do we have that? So it turns out that in the logic that we commonly use in silicon, the so-called CMOS logic, gates are naturally inverting. That is, the simplest two-input gate is going to be a NAND gate or a NOR gate. And to create an AND gate, you have to take a NAND gate and add an inverter to it. So these are what are called as inverting logics. What that means is that inverted version of a function is faster than the positive version. So NAND is faster than AND. So actually, the reason we are seeing it is that if we were to actually have an AND and not have that bubble, it would actually be faster because, it would actually be slower because I'll have to put inverters there to make that happen. Okay? But that's an artifact of this particular way we design things. Okay, you could imagine in some non-electrical technology or perhaps even some electrical technologies for different nature, positive gates might be faster. Okay. Any other question on this? Okay, so
So combinational logic we are done with, in the sense we know now what the delays are, we can do all this accounting and all. So let's move on to what we are really after, which is how fast can I run my system? How fast can the clock go? And that basically says that we need to say something about the sequential logic, how well it is working or not. So let's again go back to our generic example of a sequential system, so which we have seen many times. So we have a state register, we have some combinational logic, and at this stage, whatever complicated combinational logic I throw your way, you can always work out its contamination delay and propagation delay. Okay, so we know that. So I have input coming in, I have some output going out, I have next state, I have current state, and they all of them are multi-bit thingies. So if I now if I were to uh, uh, look at what are the timing characteristics of, so combination logic we understand, but let's look at the flip-flop. What are its timing characteristics and all? So thus far we have had a very idealized picture of a flip-flop, right? It has a clock, an edge comes, it grabs the input, puts it on the output, and also, by the way, remembers it. But if you analyze it lower at a circuit level and all, obviously there are going to be delays and all, and the question is how do we characterize it? So this figure is an attempt to do that, and it's a little bit tricky. So so let's make sure that we kind of understand it. Okay, so I have the uh, I have the data input out here, the clock out here, and the output out here. And my data has some value, x, in this region, some valid value. It has something else before, sometimes something later, it again changes. I don't know what it is. I don't care what it is. But I have some value x out here. My clock tick comes, and as a result of the clock tick, Q changes. And as we have repeatedly seen, once we have a multi-bit signal, then they don't change simultaneously. So Q will begin to change at this stage, and Q settles by this stage. So that leads to a few very important parameters about the flip-flop. So one important parameter is the contamination delay from C to Q. From the point the clock arrived to the earliest point in time that Q begins to change. So it's the contamination delay from C to Q, from clock to output. And the other one is the propagation delay from the point the clock arrived to the point that the output got settled. And both of these are under the assumption that the input was not changing. Okay, so input was stable, clock arrived, and the output changed. So thus far it looks like combinational logic. But we made a very key assumption, which is input is not changing. So what does that mean? So if we look at flip-flops in their most native, kind of deep at the circuit level, what they're really doing is they're sampling a signal, right? When the clock comes, then they're saying, let's observe the input. And whatever that input is, I'm going to copy it into the output and of course remember it. Now, think about like how you might do something like this. I'm trying to observe a signal, but if the signal itself is changing, my task would be pretty hard, right? I could capture it in the midst of it being changing. So I have to make sure that the signal is not changing, because if the signal is changing at the time I'm sampling it, then I may get neither 0 nor 1. I may get some input intermediate value, and then my flip-flop may get stuck in some weirdo analog state, which we want to avoid. And in fact, a key cause of failure of digital systems is precisely that a flip-flop happens to look at the input signal when the input signal was changing. And remember, these are electrical signals, so while logically we think of them as 0 or 1, but electrically they are going through the full range of voltage values, and if I happen to sample it at the wrong time, then I may get a value which is neither 0 nor 1, and my whole circuit will go into, as I said, a weird analog state, which is referred to as metastability. Okay. And roughly speaking, you can think of as 0 and 1 represent two stable states of my system, and metastability represents kind of a state of my system which is quasi-stable. It's stable, but a little bit of perturbation, it will go take either way. So it's kind of like the peak of a mountain. I'm just hanging at the peak of the mountain. You shove me, I will fall either way, which are the zeros and ones are the valleys, and we're kind of stuck out there. Okay, but the point is that if I happen to sample incorrectly, then we can be at that peak and stay there for a long time, and the hardware fails. So metastability is to be avoided at all costs. So the way it is done is that flip-flops put guidance on how much before the clock tick the signal should become stable, the data input, and how much after the clock tick it should remain stable. So basically we are going to disallow the data input from changing near the clock edge. It should remain stable, leading a teeny bit before the clock edge, and continue to remain stable a teeny bit after the clock edge, thereby maximizing the probability that metastability won't happen. Okay, that is, we'll sample the signal at a stable point. Remember, I said probability because it turns out you cannot, it's a probabilistic phenomenon, so you cannot eliminate it, but by having a sufficiently large window, you can drive down the probability to be very, very tiny. But working against us is the fact that we have tons of flip-flops in the system, in a reasonably sized digital system, and we use them over long periods of time. So even if my probability for metastability is very low, summed over all the flip-flops and over all the time, it can still add up to a reasonable failure rate, and therefore people who design these things, they talk in terms of mean time between failure. You want to make sure that the mean time between failure of a flip-flop from your system start to the first failure of a flip-flop is longer than something reasonable that you kind of pick up. Okay, so going back out here, that leads to these two key parameters, Ts and Th. Ts represents the time for which the input to the flip-flop should be stable prior to the clock edge, and T sub h represents the time for which the input to the flip-flop should remain stable after the clock edge. So that is what, so it's sampling the clock, so it's stable time before the clock edge and Th is after the clock edge. S stands for setup and hold, H stands for hold. So setup time is the time before the time relative to the clock edge by which the data input must have been set up, and then we have to continue holding it for T sub h after the clock edge. So, and then we already talked about Tc sub q and Td sub q. So we have these four key parameters then: setup time, hold time, contamination delay from clock to output, and propagation delay from clock to output. The setup and hold times are the tricky one because to appreciate the reason really kind of goes into what is really happening deep down, this act of sampling, okay, observing a changing phenomenon. And we are basically saying if you try to observe, if we force the circuit to sample a changing signal, bad things happen, and therefore we need to create this buffer zone around that time so that we don't run into any issues. Any questions on this? Okay, so setup time, hold time, contamination delay, propagation delay. So our flip-flop has these four parameters. So now let's look at what happens, how these things play out on my overall state machine. So let's imagine that I have a state machine which looks like this. It has 2 bits of state registers, so this and this, and it has 2 pieces of combinational logic as shown. One is a fast one, min, the other is max, a slower one. Okay, so min and max here are different delays. The min has lower delays, max has faster delays. And I have these 2 flip-flops. So let's think about how these setup and hold times play out. So remember what we said. We said that at the clock tick, the flip-flops take the new state. And that happens at every clock tick. At every clock tick, they are going to update the state propagates, the next clock tick happens. Okay. So, and these are logic delay. Okay. So now let's think about how setup and hold times play out. So let's consider a path which starts from the clock at the top flip-flop, goes through this yellow thing through the larger delay logic block, and then back to the, then to D out here. Now remember, upper flip-flop is going to give me a propagation delay, that is from clock to Q. It may take as much as TDCQ time for the output to get settled. Then this guy, the combinational logic, may introduce a delay of TD max. And only after that, this plus this time, after the clock edge, would my signal be available at the point B. But I also have to make sure that B is ready, hold time, setup time prior to the clock edge, right? Because the next clock edge at the lower flip-flop, it has to see sufficient amount of hold time. So I also need to budget for, sufficient amount of setup time. So I also need to budget for that. So I have the delay through flip-flop, delay through combinational logic, and delay through budget for setup time. And all of that added up should be less than the clock period. Because if it is not, then the clock tick at the next clock tick at the lower flip-flop will arrive while my signal has still not reached a stable state. And this property should be true for every pair of flip-flop in my system. If any one of them sees a violation of this, then the destination flip-flop will latch will get the incorrect value. So for every pair, for all pairs of flip-flop, including any self loops. Okay, if a flip-flop has a state going through some combination logic and coming back to itself, this property has to hold true. So this, as you can imagine, places a lower bound on the clock period, right? Each such loop in my system is placing a constraint on the clock period, a lower limit, and my clock period has to satisfy all of them. So that basically will end up saying something about how fast the system can run. So what that means is, if my system is failing because of a cause like this, then I really have two choices. One is I can slow down the clock. The other is to do what? Huh? Make the combination logic faster. How can you do that? I guess none of you are gamers and all, huh? Huh? Overclocking. And what do? They freeze the thing. They put their computers in sort of this cooler environment and all, because cooling it makes it faster. Okay. So you keep the, so overclocking is enabled because by cooling it you are reducing the delay, and therefore you are reducing the right hand side, and therefore you can overclock. Okay. So setup time constraints basically deal with this issue, and the bottom diagram is showing that pictorially. So at the first clock tick, the upper flip-flop basically started this whole process. After some time, A got settled, so that's the DCQ. Then A flows through the wire, and then there is going to be some amount of time at which point B will become settled. So at this point, B is settled, and then we have to budget for the setup time. Okay, and then then we budget for the setup time, and then usually there is some additional budget, some extra time that you will leave there, which is kind of your slack. Okay, that you can still so if you can start reducing the clock period until you see a violation, and that's the fastest your circuit can go. The maximum value of this that we see anywhere in our circuit, that is a combinational path starting at a flip flop and going through some combinational logic and ending at a flip flop. The longest such path that I see is called the critical path. So critical path is the path which is the worst case one. So in this diagram, we have two paths which exist, which start at a flip flop, end at a flip flop. The other one is starts at C, goes through min, ends at D. We did not talk about it, but we'll have a similar constraint coming from there, and we are going to take the worst case of the two. Okay, so let's take a 5-minute break, and then we will talk about the hold time, the other constraint that we had on the flip flop and the row experience. But let's take a short break. Okay, so let's restart. So what we saw was the role setup time plays, and essentially it places a constraint on how fast the clock can go. And if we see a failure because of this reason, then basically what the effect of that would be that you would see incorrect values getting into the flip-flops, and then the solution to that would be to slow down the clock or to do something else. Now, unfortunately, uh, uh, if a failure like this happens, it could be pretty tricky to detect because deep down in the hardware, somewhere, some flip-flop is getting a wrong value. So a lot of testing and all is done. There are circuits, there are special circuits which are buried in the hardware to help diagnose these issues. So for example, one very common thing which is done in our processors and all is that every flip-flop in the system is chained together. And kind of the idea is that when you suspect when you're trying to debug, then you basically give one clock tick. And then you extract the state of all the flip-flops and examine it. Then you do one more clock tick and do the same process until you identify what might be happening. So there are special test ports which exist on the chips which help you kind of do that. You might have, if you've ever played with hardware, you might have heard this term called JTAG, okay, which is kind of a special port for this purpose. So that's one issue. The other issue is that what this also says is something about how you should do the design. Remember, this property has to hold true for every path which starts at a flip-flop, ends at a flip-flop. Which means that I may have a situation where 99% of my paths are all okay, low delays, but there are few which have very high delays, and they will become a bottleneck. So ideally, what you would like to do is to create a situation where all your paths are roughly equal, okay? Because if a combinational logic is too rapid, too fast, it's not doing me any good because something else is holding up my clock anyway. So I can think of it as one of two ways. One is if parts of my design are too fast, maybe I can slow them down. I can lower their voltage, or I can use some slower logic, which is better, which maybe have fewer gates or something like that. So I could play those kind of games also. So just this insight helps a lot. Tools of the type that we use, synthesis tools and all, which Paul and Salma made references to, when you give them your Verilog code and all, they output these things. They also give you estimates of all this stuff. So they tell you what's the clock cycle is going to be and all to the first order. Of course, these are all models, estimates and all. A lot of effort has also gone into on doing things a little bit more dynamically. So at runtime, somehow figure out what is the fastest my hardware can go. So currently what happens is we design hardware, then we, based upon simulations, testing, estimates and all, we kind of figure out, okay, this clock speed is safe. And then we run it at that. The problem with that approach is that every piece of hardware that is made is different. The transistors are not manufactured exactly the same and all. And the other thing is they're operated at different times. My computer may be sitting in a heated room and your may be in a nice air conditioned setting. They will experience different kind of delays. Also, over time, the computer circuitries age and they slow down. So wouldn't it be nice if my computer could magically figure out what is the fastest clock speed at which it can run correctly and then just run at that. So there are also sort of types of designs and all which try to achieve that. And then finally, if things do go bad, then maybe we can have some sort of a recovery mechanism. So a pretty cool piece of work out of University of Michigan a few years ago, something it's called a razor architecture. What they do is the following. For every flip-flop, they have a shadow flip-flop. And it takes a clock a little bit later. But the idea is that the first flip-flop, so we are optimistic, and so the first flip-flop is taking the clock earlier and it tries to move ahead. But if things go wrong, then the second flip-flop will see a different value than the first flip-flop. And in that case, we do some sort of a rollback, we recover, and sort of essentially throw an exception to the operating system and then do some recovery from that. So this is an area where people sort of try to optimize a lot, because if you don't, then you are leaving a lot of performance on the table. Okay, so this was an easier story. Let's move on to hold time, because it's a nastier one and unfortunately things are not as easy there. So now we are going to look at the other path in our system, which starts at the flip-flop, goes through the fastest delay in the combinational logic. So in this case, it starts at C, goes through the minimum logic delay component up at the top, and then ends up at D. So now let's see what will happen. At this clock, we basically start seeing after the clock tick at this here, we'll see C change, and it can change as quickly as TCCQ, contamination delay. So C changes at this point, and then C will eventually stabilize too. But when C begins to change, then D can begin to change very rapidly also. That would be TCCD. That's the time contamination delay from C to D. So that's this component. And remember, our flip-flops also have a hold time requirement. So this clock edge out here has a hold time requirement. So the same clock edge, when it had appeared out here, it requires that D should not change for a period TH after the clock tick. So what if TH was such that it was more than this point? That is, D begins to change, because I'm looking at how rapidly D can change, and maybe D changes too quickly. I'm still in the hold period, and that would be a bad thing. So I need to make sure that my fastest delay is slow enough, right? From the point the flip-flop changes and its effect propagates to the combination logic, we want to make sure that the inputs of the flip-flop don't change too quickly, because if they change too quickly, I'll see a hold time violation for the same clock tick at some other flip-flop. So what it's saying is that the contamination delay through the flip-flop and the contamination delay through the circuit, the fastest contamination delay through the circuit, should be greater than the hold time. Because if they are not, then I will see a hold time violation, and again the flip-flop will see some bogus value. So now let's look at this constraint. It's a function of, it has nothing to do with clocks. Note that firstly, right? There is a clock period is not entering into the picture here at all. It's only about the flip-flop property, combinational logic property, flip-flop property. And this unfortunately is nasty, because let's say this is violated. What can you do? I mean, other than replacing my flip-flops, I mean, it's not like I can slow down the clocks or do something else. I'm kind of stuck on this one.
Can't you add different states in combination
Huh?
logic? Can't you add like
Yeah, but that means going back to the design. So I'm saying you cannot do anything once you purchase your chip and you have a computer good to go, right? So yeah, so you have to make sure that hold time failures do not happen at the design time itself. You'll have to make sure that there is sufficient margin so that under worst case conditions of temperature and stuff like that, you are still in a temperature, aging, manufacturing variations, all sort of issues which can affect the delays. You have to make sure that under the worst anticipated scenario, you don't have any hold time violations. These are a pain to detect, okay, and the violations are particularly nasty because if the setup time were violated, maybe you can tell the customers that just run the thing slowly, okay, or maybe we do better cooling or something like that. Here you are kind of stuck; it won't work. So these are particularly nasty. We cannot fix them at all by just slowing them the clock. You have to kind of revisit the design pretty much, okay, or find some other clever way. I mean, like, so your intuition is right that I have to slow down the fast parts now. Okay, so let's look at an example. Again, this is one of those things you should be very comfortable with doing for purposes of finals. So make sure that you solve these kind of problems. The book has plenty of them in the chapter. So what we are given are some characteristics out here. So we are given that T dCq, T ccq, and T sub s, they're all 150 picosecond. T sub h is 250 picosecond. TD max is 850 and TC min is 100 picosecond. Our circuit is exactly the same as before. So first question, is the hold time criterion met? So our hold time is 250 picosecond and we wanted the hold time to be, so remind me, what were we looking at? So what are we comparing hold time against? Minimum time. So what's the minimum time that we are going to look at? Through flip-flop and through the combinational logic, right? So it's going to be 150 plus 100. And we want to make sure that this thing is longer than the hold time. So we want to make sure it's greater than equal to this. In this case, it is just met, unless I screwed up on my math, but yeah, seems like okay. What is the minimum cycle time, minimum clock cycle that we can have? So now we have to look at the longest one. So in that case, TDCQ, which is 150, plus maximum time to the combination logic, which is 850, plus the setup time, which is 150. So that would be 1150. And my clock cycle should be at least that much. Okay. So this is what, some close to gigahertz type clock speed out here. So now in a given problem setting, any one of these variables may be like, it may be that the clock cycle is given to you and you might be asked what's the setup time that you can tolerate, those kind of things and all. Okay, so there are several variables, some of them are given, some others that you will have to play with. Okay, let's see. Yeah. So consider another example that I have a flip-flop with setup time of 50 picoseconds, hold time of 40 picosecond, and both contamination and propagation delay of 60 picosecond. And we are using it to implement state register of an FSM. The next state logic has a propagation delay of 800 and contamination delay of 50. Compute the setup and hold time slack for this arrangement. So by slack we mean how much margin we have. So how much can I increase the setup time and still be okay, and how much I can increase the hold time and I am still and still be okay. So one thing hopefully you have realized is that a good flip-flop is one which has a short setup time and a short hold time, right? Because that imposes the least constraints on our design. So let's go to this one. So the slack on the setup time would be the clock period minus this term, the maximum delay through the system. So 1000 is my clock period because we are told it's 1 gigahertz, minus 60 for the delay through the flip-flop, 800 is the delay through the combination logic, and 50 is the setup time. So end up with 90 picosecond. That means that I can trade this flip-flop for a flip-flop which has 150 picosecond setup time, 140 picosecond setup time and still be okay. Or alternatively, we are saying that I can increase the clock speed so that the period goes down from 1000 to 910 and I'm still okay. So that's on that side, and on the hold side you can similarly calculate what is my fastest time minus what is the hold time, and that's the slack. So I have a 70 picosecond of slack which appears on the hold time side. What again it is saying is that I can use maybe a cheaper flip-flop and still be okay. So the question there? No. Any questions on this? So a lot of bookkeeping, but basically sort of those two key equations, one for setup time and one for hold time, and then how to calculate the contamination delay and the propagation delay. It's basically the marriage of these things which yields all this analysis. Now, real life obviously is never so idealized, so there is an additional complication which sort of comes in and which I alluded to you earlier as well, which is the clock itself reaches the flip-flops at different times. Okay, so my flip-flops are scattered all over a large chip. Clock enters the chip at one corner and then is distributed all over the chip. Now, what people try to do is they try to make the wiring such that the clock reaches all the flip-flops at the same time, but it will never be perfect. So if I were to somehow magically observe the time difference between the clock edges reaching the different flip-flops, I'm going to see a spread. Furthermore, clocks themselves, the clock sources, are not perfect. So when you observe a quartz crystal oscillator, the clock coming out of it, the edges jitter. Okay, what I mean by that is, if I have, let's say, a gigahertz clock, then you would think, okay, edges are 1 nanosecond apart, but that's not always perfectly so. One clock edge may come a little bit earlier, the next may come a little bit later, so the clock edges kind of jitter a little bit. And that happens because there are fluctuations in voltage, and temperature changes, all sort of weird physical things which happen. So net result is that you cannot say that clocks reach simultaneously, clock edges are observed by flip-flops simultaneously. That's never the case. So let's attempt to model that part. So let's imagine that I have a clock source and the bottom flip-flop gets the clock a little bit earlier or a little bit skewed relative to the other flip-flop. Okay, and we model that part as t sub k. So we are basically saying that if the clock arrives here at t, then it arrives here at t plus t sub k. And you can imagine that tk could be positive or negative, but let's, for the sake of argument, just assume it's positive. Okay, so the upper guy is getting the clock a little bit earlier. So now what will be the impact out here? So remember, what is happening is that the clock at the upper flip-flop is, if tk is positive, then it is delayed. So let's look at the implications of that. So remember, our setup time was being decided by this guy, this path, which started at top flip-flop, ended at bottom flip-flop. And what it is saying is that is TDCQ plus TD max plus T sub, TS should have been less than TC5 normally. But since the clock here arrived later, so I have eaten into my clock cycle, right? Because the source flip-flop started a little bit later, whereas the destination flip-flop, its clock edge is coming earlier, relatively speaking, right? So I am eating into my budget, so tk will appear on this side. So skew in the clock has the, in essence, is serving to eat out of my clock budget. Okay, and what you would usually see is that they'll say after your chip has been laid out or the wiring done and all, you'll basically get some number saying this is the maximum skew possible, or your FPGA may tell you that, and then you budget for that in this manner. Okay, so it's basically out of each clock cycle you have to set aside the time because of the skew. What about the hold time? Well, for hold time, remember it was the other path we were looking at. So for hold time, we were looking at this path, fast path. Now, remember the problem in the hold time was that because the change triggered by the lower flip-flop reached the top flip-flop while the top flip-flop was still in its hold regime. But we are making the situation worse now because the upper flip-flop, its clock is delayed. So therefore, its hold period is delayed. So what is now going to happen is that my constraint becomes, as shown out here, TCCQ plus TC min minus TK. So right hand side is actually being reduced if TK is positive, and that is bad because that means I can violate P sub h. So skew is bad. That's kind of the moral of the story out here. Now, of course, if I knew that this was a worst case, if on the other hand, let's say the delay at the clock at the bottom flip-flop was delayed, what do you think it will do to us? So, or another way of saying is TK is negative, right? So, so that would actually help us if you think about it, because if this TK is negative, then I'm really adding a number out here. So it could actually, it helps us in hold time situation like this, and it is going to help us also in the clock tick cycle. I can actually speed up the clock. Okay. Now, when you design the chip and all, depending upon how the wires get laid down on silicon and all, things may go either way. So you would be conservative and think of the skew as something you are taking out of the budget. But by cleverly playing with it, you could also use it to your benefit. Not a great design strategy, but nevertheless one could do that. Now, in all of this, I'm also ignoring a lot of other effects like wiring delay in the data signal itself and all. So there are a lot of other additional complications which come in. Again, this kind of analysis is beyond sort of human ability to do when you are talking about big chips with billions of gates and all. So of course, tools do it for us. Okay, but it's very essential to do it because what you don't want, particularly what you don't want, are the hold time violations. Because once your chip is fab and it has a hold time violation, you really don't have any easy recourse at that stage. Okay. So we could repeat the same example we had a couple of slides ago, except that now I have a, okay, ran out of ink in my pen here, but basically, we basically have to budget for that, and so the 75 picosecond eats away into the slack we have for setup time, and also eats up into the slack on the hold time. In this particular case, with a 75 picosecond skew, we actually are facing a hold time violation. Okay, and that kind of made sense. Previously, we had a 70 picosecond slack, and we are making a 75 picosecond skew. So our hold times are violated now, and the design won't work. Okay, let's pick another example. Let's see. Okay, so we are again given 150, a whole bunch of things, but my skew is 100 picosecond. I think all the other parameters are the same. 100, no, they have changed also. So is the hold time constraint met? Anyone?
Yes.
And can you say why?
150 plus 100 minus
Okay, so fast path 150 plus 100, that's 250. And so we are looking at the hold time. So hold time we actually subtract, right? I mean, if you go back to the equation, we subtract p sub k. So okay, so 150 plus 100 minus 100, so we are left with 150, and our hold time was 250. So we are entering into a problem out here. Okay, what about minimum cycle time? What is the minimum cycle time? So you look at the max. So 150 plus setup time, that's another 150, that's 300, plus 850, that's 1150, and the skew is added, so it's 1250, and that's going to be the minimum time that you're going to have. Okay. So this is some combinational logic. What is this guy doing? Anyone? What does this circuit do? So every clock tick, what is the combinational logic doing? If I call my state or whatever output of the state register to be X, then this it is a counter, it is adding something, but what is it adding? What is it doing? So it's taking the previous state, it's feeding that to input of the full adder. The other input to the full adder is the previous state shifted by 1 with a 0 fed in, right? So if you look at each one of the bits, so the like the full adder, this full adder, this guy, okay, is getting the previous bit and is getting the bit from down here. So it's so ith full adder is getting xi and also x minus I minus 1. So it's as if I am adding x with x shifted by 1. X shifted by 1 is 2x. So I'm really doing x plus 2x, right? So if my current state is x, I'm basically computing 3x, and that would be my next step. Okay. So that's almost an aside. So again, you're given delays, you're given the minimum characteristics of the flip-flop, and then question is the hold time constraint met? You can work that out. In this case, yep. Is the minimum cycle? You can calculate that. In this case, the trick out here is that there are lots of paths, like there are tons of flip-flops, but they're very symmetric. Okay, so you basically just have to focus on one and can do. Can a skew of 20 picosecond be tolerated? So again, you plug that into the equation. You basically end up with that the whole time is violated, so that cannot be tolerated. What can one do? So again, for violation of setup time, we can slow down the clock. For violation of hold time, really you have to redesign the flip-flop, you have to reduce the clock skew, that's another possibility. Neither one of them are practical in the sense that these are not things you can do once the chip has been made. You can do these things while you were still designing the chip, but you cannot do later. So again, I guess moral of the story is that hold time is something you have to be much more diligent about, and it's harder to also kind of figure out. Okay, another one which was what was suggested out here, that I artificially put additional logic just to slow things down. Okay, so all those strategies could be done. Okay, so to summarize, in digital systems, we see several kind of delay related issues. So firstly, in combinational logic itself, we have propagation delay and we have contamination delay. Flip-flops introduce two additional factors, setup time and hold time. And cycle time is determined by the given equation, hold time is given by the other equation, and clock skew affects both. Now, one other thing I also wanted to bring out is that setup time and hold time need not be positive. So thus far, we kind of, the way I presented, the way book describes in the chapter, you kind of get the impression that setup time and hold time are always positive, because I described it as things being stable on either side of the clock tick, right? And that would lead to the impression they should be positive. But unfortunately, things are not as simple, and the reason they're not as simple is the following, as to how flip-flops often get packaged. So let me talk about that a little bit. Okay, so let's imagine this was my flip-flop. And it would have, this is a base flip-flop, the smallest entity that you can imagine, and of course it will have positive hold time and setup time, because that's how flip-flops behave. So if I look at just this guy, then T sub h and T sub s are going to be greater than 0. Okay, so if that's the flip-flop you were getting, things would be fine. But oftentimes, that's not what you buy. The flip-flop that you get may be packaged with other stuff, and that's what you get. So let's imagine, for the sake of argument, let's say what happens is that the flip-flop that you actually buy has some combinational logic here, so some logic here, and this is the flip-flop that you're buying. That internally, the red flip-flop that I'm buying internally consists of some combinational logic and some real flip-flop. Okay? And now, the setup and hold time are going to be described for this new input. Let's call it some d prime. And they're going to be described with respect to the clock I'm seeing. Now remember, the internal input, the real input of the internal flip-flop has a positive hold time and setup time. But this combinational logic that I have put is going to cause some delays. So anytime my input, I provide an input out here to d prime, is going to take some time to reach d. So what would it, so if I look at the setup time of d prime versus the setup, remember the clock is the same. In both cases, the clock is the same for the internal guy and the way I look at it outside. D had some setup time and hold time, but I added this combinational logic, and let's say its delay is delta. What do you think would be the setup time of d prime? That is, what can I say that how much should d prime be stable for before the clock ends? So let's say my requirement, let's say the green flip-flop said setup time is 10 picosecond. Okay? So that means that the D input should be stable 10 picoseconds before the clock edge. But now I have this combinational logic. So what can I say about D prime? How much before the clock edge should D prime be stable? Anyone? 10 plus delta, right? Yeah, 10 plus delta. Okay. So setup time has increased. What about hold time? So let's say the hold time was 10 picosecond for the green flip-flop. What can I say about the hold time of D prime? So remember, we want D to remain stable for 10 picosecond after the clock edge. For that to happen, D prime needs to remain stable for, so the thing is, since D is changing later than D prime, so I can basically say that my D prime is more relaxed. I can actually have a hold time of 10 minus delta. And if delta is sufficiently large, I can act, seen from D prime's perspective, is as if I have a negative hold time. I can play the same game in the reverse direction. Let's imagine a flip-flop where the clock had some delay added out here for some reason. Maybe a lot of wiring delay or something like that, or maybe the clock was buffered. In that case, the reverse thing can happen. Setup could become negative. Okay, and hold may increase. Main thing that matters is that setup plus hold will be constant. And the effect of all these other things is to shift that budget around. Because what you normally get as a unit is not really that bare minimum flip-flop, but it's that flip-flop surrounded by other stuff. So this concept of hold time and setup time are things we can talk about for any sequential logic. I give you a sequential logic and you can define for me, for a given input relative to the clock, when can it change. So the concept of hold time and setup time are about sequential systems in general, not just about flip-flops, because they are basically telling me when am I at a liberty of changing the inputs. Now, normally signals come from another circuit, another gate, a preceding gate, and therefore I can control very well whether I'm meeting the setup time or hold time or not, as we talked about. Can you think of some setting where it would be essentially impossible to meet setup and hold time requirements? Now, remember, it is not about changing faster, it's when they change. So think about under what circumstances you really don't have any control over when they change. Real world input, exactly. I mean, the user is pressing a button. I cannot tell the user change it with setup time or hold time in mind, right? The user is going to press the button whenever it wants. And that creates a real problem, because I also told you that all of this is a probabilistic game in any case, but furthermore out here I cannot even guarantee. External world input is going to come when it wants to come. So that obviously presents a very serious problem, that things coming from outside, if you just feed to your flip-flops like that, then you are pretty much asking for trouble, because you are going to see violations sooner or later. Now, one thing you can do is you can make flip-flops which have very low setup and hold times, okay, because that's the only strategy that will work. You're going to minimize the probability. But they are costly and not easy to do. But what you can do is to create flip-flops which are designed for this manner, where the probability of bad things happening is low, and keep them at the boundary of your chip. So when your external world signal comes, it first goes to these special flip-flops and only then goes to rest of your circuit. So rest of your circuit can be designed assuming that things have been cleaned up, and these sentinel flip-flops kind of take care of stuff around that. So this is, by the way, a flip-flop which has gone into that buzzer state. Okay, so basically you put an oscilloscope probe, you'll see noise. Okay, basically it's fake. So anyway, we're done with this topic. We'll see you next week.